In the last video, I talked about how Thomson would shoot a beam of charged particles through this glass tube and determine its velocity using this formula by measuring the electric field and the magnetic flux density that would cause the charged particle beam to go straight through the parallel plates. Now let's see how we can do the next part of the measurement and find this charge to mass ratio. So having found this velocity of the particle, we then the next step is then to remove the magnetic field and measure the bend angle. So let's do that. Okay. So once the let me write out the velocity here. We'll need it afterwards. The velocity of this particle is 1.875 times 10 to the power of 7 meters per second. Okay, so once we remove the magnetic field, the electric force would cause the negative charge to bend upwards. Okay, so this would go upwards, which means that the green spot here would move up. Okay. And it is possible, therefore, to measure this bend angle. Now, suppose that this bend angle, I'll call it theta. Suppose that theta suppose that theta is measured to be okay, 14.04 degrees. How can we then use this to calculate the charge to mass ratio? Right, in order to understand this, let's look at what happens here in a little bit more detail. Okay, I'm going to magnify this. I'm going to draw the positive plate there, the negative plate here. Now, and the charged particle, charge Q, mass M. As it goes through, it bends upwards. It bends upwards because of the electric force acting on it. So suppose that as a result of the electric force, it undergoes an upward acceleration. So by the time it reaches here, by the time it goes out from the parallel plate, it would have okay, it would have acquired a vertical component of velocity, which are called uy. Now it still keeps the same horizontal velocity here, the ux that we calculated, that we measured. So there's this so the ux, the horizontal component, has not changed because the force here is upwards, upward force. There's no horizontal force. So ux stays the same. So when it comes out from the parallel plates, ux is still the same as before, but it would have gained a vertical component because of this vertical force. And the angle that we could measure would be directly related to these two components, simply by drawing this rectangle, because the resultant velocity would be the sum of the two component vectors. Okay, so that angle there would be theta. In other words, theta must be related to these two by tangent. Okay, so we must have tangent theta is equal to uy over ux. Now we already know what's ux, that was measured just now, and theta has already been measured. That's this 14.04 degrees. So what remains is to think about uy and see if we can relate that to the charge and the mass. Okay, now uy comes from this force. So to calculate uy, let's think about its acceleration, its vertical acceleration. Now we know how uy would be related to the vertical acceleration, which I'll call a. Okay, vertical acceleration from the force. uy, when it first enters, there is no vertical component of the velocity, it's just horizontal. And by the time it leaves the parallel plates, it has gained this vertical component. So suppose that the time taken for it to go from there to there is t. It's the time t to travel through the plates. So uy must be equal to the acceleration times time. Right. Now, and the acceleration can in turn be related to the force acting here, by force over mass. That's the acceleration. And the time t can actually be related to the horizontal velocity and the length of this parallel plate, which are called L. I've not actually said what L is, so I'm going to take as an example 10 centimeter for L. Okay. So to find the time, if we know the distance traveled and the horizontal velocity, we would take the distance and divide by the velocity. Okay, so if you look at this, we know L, we know ux, but we don't know F, we don't know M. Okay, and still remembering that we want to relate this to Q and M, we see that M has now appeared down here. Now F must be related to Q by, by the electric field. We know that force is equal to charge times the electric field strength. Okay, and that the electric field strength is in turn is in turn equal to the voltage across the parallel plates, not that voltage, not that one, I'll call that V0, but this one, the voltage here, which I'll call just V. Okay, the voltage divided by the distance in between. So let's say the V here is the 100 volts and the distance in between, the D here, is 2 centimeters. That be 2 centimeters. So with these numbers, we can find V over D. We can find the electric field. So let me put this in. So the F here will be QE over M. And now we know that we can find E from V, the voltage, and V and the spacing between the parallel plates. So QE over L UX. We can now put this equation into here. Now, notice that Q has now appeared. So I actually have the Q over M here, which I want to find, the charge to mass ratio. Okay, so and this is UY. Now, charge to mass is the unknown that I want to find, and we know E, we know L, we know UX, we even know theta. So this means that if I substitute this into here, I should be able to find Q over M. So let's do that. Tangent theta is equal to, okay, so substitute this whole thing into the U, Y, F. Q over QE from here and the L over M UX, that would be the UY going into there, and we have another factor of UX at the bottom, so that would give me a UX squared here. Right. So, okay, so now I can make Q over M the subject by rearranging this expression. Move M UX squared over to the left. And I would have E L over to the bottom. That's UX. Okay. Now, oh, yes, well, actually, I don't want the M. M has already come down here. So let me clear that out. Yes, right. So rearranging this gives this expression. And let's check again. UX, we already know. It is that value there. Theta, we know. It is the measured angle. So UX and theta has both been measured. L, we know. We can just measure the distance between the plates. E, we can find just by taking the voltage over the spacing, V over D. So putting all these numbers into here, we can finally get an answer for the Q over M. The answer is 1.758 times 10 to the power of 11. Now it's a charge to mass, so in SI units, charge is coulomb, mass is kilogram. So that would be, the units would be coulomb per kilogram. And I've been calling this the charge to mass ratio. So let me write this out. Charge to mass ratio. Now there is another commonly used name for this quantity, for the charge to mass ratio. It is also called the specific charge. Now, in physics, the word specific also has a specific meaning. It does not mean the same thing as we would when we use the word in everyday conversation, where we would just mean something. If we say that something is specific, we just mean that we are talking about something particular, something definite. Now, that's not what it means here. In physics, the word specific has a different meaning. If you have learned about specific heat capacity, you would know that it means the heat capacity per unit mass, per kilogram. So specific actually means per kilogram. And in this case, specific charge means the charge per kilogram, which is exactly what it is. If you look at these units, it's coulomb per kilogram. And if you look at the formula, if you look at the meaning, it's charge over mass. When you divide by something, you get per unit of that thing. Just like when you divide velocity, when you divide velocity by time, you get per unit time. So when you divide charge by mass, you get the charge per unit mass. So that's exactly what the word specific here mean. Okay, so let me just write up this part just to make sure that that's very clear. So the word specific means per unit mass.